Hello, I'm Dr. Levon Hayrapetyan, a business professor at Houston Baptist University. In this short video, I will show you how to calculate z-scores of variables, which helps us to normalize variables when they are in different scales. Let me explain the essence of this. So we already calculated in previous video. I showed how we can calculate Euclidean distance between these three observations, and these are the numbers which came up with. These are the measure of similarities or dissimilarities between two observations. Now, if you look at the numbers here, see age, the value of age is 45, 46, 40, very small numbers compared to annual salaries, which are in thousands. And that's why in this case, the values are in very different ranges and scales. Therefore, the annual salary will significantly dominate the age in our calculations. That's why it's very common to standardize the units of each variable and replace them with the z-scores. Normalization is a good tool when the values are in very different scales. So how to calculate z-scores? Basically what we will do, we will replace each variable by its z-score or z-value, this variable with z-value. This is the formula how we calculate z-scores. So for each value, we will calculate the value minus the mean of all variables in that category, divided by standard deviation of those variables. So I will go and do this in Excel. Let me switch to Excel. So this is the spreadsheet which we used last time when we calculated Euclidean distances between observations using this formula. Now what I will do, I will calculate z-scores of all these values and get them in here. But in order to calculate z-scores, as you remember, we need to have the mean and standard deviation first. So let me calculate the mean of ages. The function which is used to calculate the mean in Excel is called average, very commonly used function, average, and average of these. So the average age is this. Then, so this will be mean. Now, then I'll calculate standard deviation. Standard deviation. And in order to calculate standard deviation, which we will use Excel's function called stdev.s, excuse me, which stands for standard deviation, and .s means sample standard deviation. So I have these two formulas for the mean and for standard deviation for the first variable. Now I will just select this range and drag, which means I'm copying those formulas. Now here I have average of this range and standard deviation for salary. Here I have average for credit card debt and standard deviation. So I have my mean and standard deviations. Now I will normalize my variables using that formula equals. So I will start here, I am normalizing 45. It will be, wherever I have my 45, minus the mean divided by standard deviation. Standard deviation. So now if I cut equals to, obviously this is a correct formula, but if I want to be able to copy this formula down for all the variable age for all observations, pay attention. For the 46, I have to use the same mean and standard deviation. For 40 also, I have to use the same mean and standard deviation. That's why I will make mean and standard deviation absolute. So you can either manually put the $ in front of B here or in front of 8, or you can just hit F4 and it will make the absolute reference absolute. Now, and Now this is my formula, which means x minus mean divided by standard deviation. And I will copy this down. Now I have normalized values for age. Exactly the same way I will do normalized value for salary and for credit card debt. So for salary, which means I'll start with this one, equals value minus standard deviation divided by, or minus mean, sorry, divided by standard deviation. I will make mean and standard deviation again absolute, and the reason is I want to be sure that I can copy down and all of them will be correct. Let's check this one. See, this is 80,000 minus mean divided by standard deviation. And finally, I will do the same normalization for credit card debt. So it will be this minus this divided by standard deviation. And again, I will make D7 and D8 absolute. And I'll copy down. So you can check, for example, for this one, it will be 15,000 minus 14,333.33 divided by 2081.67. So what we got here, these are my original values for my variables, and these are normalized values for my variables. Now what I will do, I will calculate distances between these three observations, again, Euclidean distances, now based on normalized values. Here we calculated those distances using original data. The formula is the same. This is the formula which we will use, which is SQRT, standard square root of, now I will use these numbers. I'm calculating between Sam and Nancy, which means I will use the first two rows. This minus this square plus minus this squared plus for the third one minus and close parentheses. Oh, I made some error in here. I didn't square. And now let me move this down so it will not distract us. Now I'll do between Euclidean distance between Nancy and Tanya. It will be SQRT and Nancy and Tanya. It will be this minus this squared plus for annual difference between salaries minus square plus and difference between credit card debts minus this squared. And finally, for between Sam and Nancy, which means I will use this observation, Sam and Tanya and this observation. So formula will be equals SQRT, difference between ages for Sam and Tanya minus this square plus difference between salaries squared plus difference between credit card debts. All right, so now these are the measure of the similarities between these three observations based on normalized data. This is better measure of similarities than this, because here we based on our calculation on the original data, and in original data we have very different scales. Here when you normalize now you bring to the same level so you can compare. Again, if we compare this, what the most similarities are between Sam and Nancy in both cases. However, when we use our calculation based on the original data, then Nancy and Tanya are actually, Sam and Tanya are closer than Nancy and Tanya. Remember, smaller distance means small dissimilarity, which means they are closer, which is reversed in here. Now here, when we based our calculation on normalized data, then Nancy and Tanya are more similar than Sam and Tanya. This concludes my short video. Bye-bye.